Greetings, YouTube. Beautiful mind here on this beautiful April Fool's Day. Part of me wishes, like, man, I just wish all of this was a huge prank and like we can just go back to normal. But I'm not. I'm low key. I'm not gonna lie. Like, I'm low key like enjoying this. Like, I get to be at home. I get to do my work from the comfort of my home. Like, I got my food. I got toilet nearby. Uh, I really, for some reason, because I said toilet, it made me think of this joke. Like, everybody's panicking about toilet paper, but I really like the way Trevor Noah on the Daily Show articulated. He was like, Americans, you guys don't know how to, you don't know how to quarantine. Like, y'all panic about things you don't need to panic about. We were like, it's quarantine. I need to go ahead and change my oil. I need to cut my grass. I'm like, it's like that. It's like stuff that don't really matter. But he was like, everybody's panicking about the toilet paper. He was like, you're in the bathroom, just take a shower. I was like, thank you. To me, that makes sense. I was like, you got the water there, just go take a shower. Like I feel like a lot of cultures around the world don't really use toilet paper like that. Like they just have the water, they shower, they bathe after that activity. So not to be so graunchy or nasty or whatever. But I mean, I think it's a legitimate discussion. It's a little bit gritty, but you know that kind of stuff happens, and so I think it's a valid point. Shower, just take a shower. You'll be much cleaner. Um, but I know we're just trying to be comfortable. I just try to keep our sanity. So I totally get both sides. It's very funny to me. Let's see. So this is going to be our lecture for Cal 3. I think that let me see. Today we're going to be doing. I don't think we did 3-2 last time. I think we just did 3-1. I think that's correct. So today I want to do 3-2. I don't want to go beyond 3-4 for the week. So we'll see how long it takes us to do 3-2. If it goes quick, oh, I didn't do my prep like I would have liked to have done. I can still kind of do it on the fly. But if it goes quick, then I'm gonna go ahead and do 3-3. But I don't want to go beyond 3-4 for this week. Okay, a few notes. Be sure that I feel like you all are a little bit more mature and like you get the rhythm of GMC. So I feel like most of you all in this course are at least checking your GMC emails on a regular. So you should have already had your GMC emails forwarded to email that you check regularly. I think that most of you all have full access to Pearson. There might be like one or two that don't. So I'll be kind of going through my records to see where people are, and I'll be kind of looking for people and just checking in on people today to see how they are doing. Um, so with full access to Pearson, we just want to be sure to be getting our assignments submitted promptly. There was a request to kind of reduce the quantity of material. So I did. I didn't mind because the projected time for those assignments were about an hour. So I try to get them up there as promptly as I can. The main thing is just get those assignments submitted promptly, and we can work out the rest of it. Honestly, I just want to see that you all are pushing, doing your best, trying, and we'll work it out. Okay. Um, so I think we can anticipate a quiz this week. So the sooner we can kind of go ahead and get through section. I'm thinking about 3-4, maybe if we're doing 3-2 today. If we can do one, maybe two sections today, that'll be more than enough. I'm monitoring the time, so I'll do my best to honor the time. And honestly, you can, like, on any given day, you can just contact me anytime throughout the day during business hours. You can actually call my office phone. Those numbers do get through and come to my cell phone, so you can actually use that during business hours to reach me. You can also email me, and we'll make sure to do what we need to do. Okay. So just keep doing the best you can. We do have a tutor available. Hopefully, you're working through Pearson. We're just going to keep all the work right there in Pearson. Also on Moodle, there is a participation and honesty quiz. Go ahead and take that quiz. I'm gonna factor it into the grade, so that's something that we have to do. I can't think of anything else, so we're just gonna go ahead and take some time to move through section 3.2. So we're going to continue the discussion of the derivative. The main thing with derivative is the derivative is the slope of the tangent line at a point, right? So if you have a tangent line at a point, that represents the instantaneous velocity or instantaneous rate of change. But to me, the simplest way to quantify or summarize the derivative is the slope of the tangent line at a point. So we have a curve, we have a line. The derivative is the slope of that tangent line. Okay, that's the gist of what this discussion is about. Oh, do I want to do that here? That might actually help. Let me switch this to the presentation view. All right. So we're gonna start here with section 3.2. We'll just do it like this. I guess this is fine. 3.2, the derivative as a function. So in section 3.1, we learned that the derivative of a function at a point is the slope of the tangent line to the graph that passes through that point. We now extend the concept of a derivative at a point to all suitable points in the domain of f to create a new function called the derivative, right? So last time we were talking about what do we mean as far as a derivative at a point. Again, the derivative of a point is the slope of the tangent line at that point. Now we want to extend the derivative across all points, all suitable points within the domain of our function to create a new function called the derivative function. So far, we've computed the derivative of a function, or equivalent to the slope of the tangent line, at a fixed point on the curve. If this point is moved along the curve, the tangent line also moves, and in general, the slope changes. For this reason, the slope of the tangent line for a function itself is a function called the derivative. So as our point moves around the function, let me see, I got my laser pointing here. As the point moves around the function, the slope of the tangent line is the tangent line is going to change, and because the tangent line changes as we move around this function, then the slope essentially changes, right? So we can talk about that function. So let's look at it like this. So the derivative is a function. So we said that f prime of a, I think last time we said, is going to be the limit as this change goes to 0, as h goes to 0, of f of a plus h minus f of a over h. Okay. So now, let's look at this, the derivative function. We say the derivative of f is going to be the function f prime is going to be the limit as h tends to 0 of f of x. So last time we were using a because we were talking about it at a point, but now we want to develop a function across all of the original function to describe the derivative. So f prime is going to be the limit as h tends to 0 of f of x plus h minus f of x over h. And you actually saw me do this. I didn't even realize that I was doing it this way. Last time I think they intended for me to do it this way, but I did it this way last time, and I realized I had jumped the gun, so I kind of backpedaled a little bit. But this is okay. Provided the limit exists and x is in the domain of f. If f prime exists, we say that f is differentiable at x. If f is differentiable at every point on an open interval I, we say that f is differentiable on I. Okay, let's look at this example. We're asked to compute the derivative of f of x equals this. Now we're going to use this limit definition. Honestly, look. So the thing that's coming up that I'm excited about, there's actually a shortcut. You can look at this and get the answer, right? So the shortcut, I'm just going to do a quick demo on the shortcut. So I don't want you to get too bogged down by this limit definition. It can be intimidating. I want you to be aware that there is light at the end of the tunnel. On the other side of this, there's some shortcuts. You can look at it and you get the answer. Let me show you right now. So then f prime, and let me, I want a thinner line. Come on. Let's see, we're gonna do, dang, that's already kind of thin. Let's do this one. So then, just to do a quick demo on the shortcut, we're gonna say f prime of x is gonna be, the 2 comes down, it's gonna be negative 2x plus 6. That's gonna be the derivative function. So what this is gonna tell us, given any x, we can find the slope of the tangent line given any x, right? Now, if this is the answer, let's see how do we arrive to this answer using the limit definition. I'm going to go style and just thicken up this line a little bit, right? So that was a demo on a shortcut. Let's see this in terms of the limit definition, okay? I think we could just work with this space. All right. So the limit definition says that what? F prime of x is going to be equal to the limit as h tends to 0 of f of x plus h minus f of x divided by h, right? Notice we can't just plug in h equals 0 because we're going to be dividing by 0, and so we can't do that. So let's evaluate this limit as h tends to 0. So f of x plus h, we're going to replace all the x's. Come on. Trying to undo. It's being super sensitive. There it is. Okay. Let's go back here. And we're going to do our color like this, right? So for our example, f of x plus h, we're going to take our f of x, replace all the x's with x plus h. So we're going to have negative x plus h squared plus 6 times x plus h. So that's the first part. We're going to say minus f of x, which is, again, negative x squared plus 6x. And we're going to say all of that divided by h. Okay, I'm definitely going to need some more space. So I'm liking it. I'm liking it a lot. Let's add a page. This is awesome. You can't see these edits that I'm doing. Paper, and we want to do some grid paper. I'm always a fan of grid paper. Helps me. Okay, let's keep going. Oh, okay. I didn't even realize it was like that. So I'm going to go like this. And actually, what I'm going to do is go like this. And I'm actually going to thicken up these lines. I want these lines to be this thickness. I think that's okay. We're going to work with that. Okay. So now let's simplify these. So then we're going to say equals. So then x plus h squared, that's going to become x squared plus 2xh plus h squared. You can FOIL there. I just know the shortcut. You square the first, you square the last, and 2 times each term. That's the shortcut for squaring a binomial. Let's see. We're going to distribute that 6. So we're going to have 6x plus 6h. And we need to distribute that negative. So we're going to have plus x squared minus 6x. And then we're going to say all of that divided by h. And again, this is the limit as h tends to 0. The limit as h tends to 0. So keep in mind, the whole point is we know that we're on the right track if we get to a point where we can cancel our h's. Right? If we get to a point where we can cancel our h's. Okay. Let's keep going. So this is going to be equal to the limit as h tends to 0. Let's go ahead and distribute that negative. So we have negative x squared minus 2xh minus h squared plus 6x. Let me see. Plus 6h plus x squared minus 6x. We're going to say all of that divided by h. Now, we should notice some cancellations going on. If we combine like terms, this is canceled by this cancels this, and I think with everything that's left, we can actually factor out at least one h from everything, okay? So then if we go ahead and factor out that h as well, we'll get the following. This is going to be the limit as h tends to 0. I'm geeking, by the way. Like I'm totally having so much fun. I forgot how much I miss and how much I enjoy calculus. Like I took calculus in high school. I took AP Cal. I did okay. But it was a very surreal experience because when I transitioned from high school to college, it was like seamless. It was the exact same stuff that we have been talking about in high school. I was like, yes. I used to have so much anxiety whenever I thought about when I was in high school, middle school and high school, and I thought about college. And like I always had this, and it makes sense now. But when I was like in middle school and high school, and I kept trying to look beyond college, I couldn't see my life beyond college, but now it makes sense. I used to have so much anxiety just thinking like, man, college is going to be so hard. I'm so scared and all this other stuff. And I was like, man, I'm never going to get out of college. And I was like, oh, I see why I felt that way because I freaking became a college professor. I didn't even know that was going to happen. I used to be so afraid of college. Now I see why I couldn't see past it because that's where I was going to end up. I mean, and I actually enjoy this stuff. It's a lot of fun. I love to explore like thought and like trains of thought and things of that nature. And just exploring. And like I feel like in this society, we're so distracted. So like that's why I think this whole corona thing is so powerful. Because now it's like we were able to remove the distraction of commuting to and from work and school. So now we don't have that as an excuse, paying for gas and trying to zip all around town, going real fast, going nowhere real fast. Like I'm actually kind of geeking. I'm really enjoying it. So now we have more time to put our energy into things that are important and not waste our time on distractions. And I feel like the better we are able to remove our distractions, the more that we can kind of hone in on our natural talents and abilities. I think Kanye West said something about I'm trying to unlock my own vault. I can't articulate it. It was in one of his The God is King, or the latest album where it was a gospel album. I really enjoyed that album, by the way. And it's all the story of the human is just very interesting. I do consider myself an interdimensional being having a human experience, and like a lot of science back this. Like that's what Deepak Chopra studies. He's a neurosurgeon where he has a full medical doctor. He's a full neurosurgeon, but he fuses it with like Eastern traditions, and so he studies consciousness. It's like a lot of his stuff opens up with what is consciousness, and I was like, huh, like we all have this, internal dialogue, and we can close our eyes and listen and think and all this stuff, and like we close our eyes, and like if we were to say imagine a sunset or imagine the feel of a rose, like you can get clear vivid images and sensations in your mind. But if you open up the mind, there's not a little picture of a sunset, or there's not an actual rose inside your mind. So the question is, where are these activities taking place? Like, where is this happening? How is it that we can close our eyes and see things that aren't there, and we can hear things that don't make a sound? So then, if all signs point to us not even being really here, then more than likely we're not even really here. Like, more than likely our bodies are just avatars that we taken. It's like a vehicle that we're using while we're in these bodies. We all have this experience of being in our bodies, but there's a very palpable sense of our true essence not even really being on this plane. It's just like we're like, these are our machines, and we use these machines to navigate the earth realm while we're here. So it's like, it's kind of deep, but science is actually starting to back a lot of these spiritual traditions. It's fantastic. And so that's honestly why I study mathematics, because I use mathematics to kind of get a sense of reality. Whereas Deepak Chopra might use like neurology and the study of the brain, and like, all these experiments and all these different things to study consciousness. I just do it from within. Like another one of my colleagues, I can't even articulate the way she does it, but she was like, when she thinks about it, she's like, we're using the brain to learn about the brain. How can something learn about itself? Like, that's mind blowing when you think about it. It's so exciting. Anyway. So going on those flights of fancy. So bringing it all back, you know, to you know, just kind of being passionate. And so it's like, again, a lot of the stuff, again, I do consider myself an interdimensional being having a human experience, and it's exciting because science is actually starting to back a lot of these notions and ideas. I mean, there are experiments we can do and all sorts of stuff, and so everything, it does make sense as to why I was feeling the way I felt when I was at those ages. But it just is what it is. So using mathematics to explore reality, we can talk about concepts like infinity and different types of infinity, and that's the kind of discussion that we're having here with calculus. So yeah, just trying to bring it all back together. So anyway, so we can actually factor out an h from all of the terms, right? So then if we factor out an h from the top, what's left is the first term we have negative 2x, the next term is a negative h, the next term is plus 6, and then we're going to say divided by the h's on bottom. Okay? So now we can cancel that, and now we can apply those properties that we had discussed earlier. So now if we pass through the 0, we're going to have negative 2x. I think that only this term is going to go to 0, right? At this point. Negative 2x plus 6 is going to be our derivative. And I think that's what we said earlier. You see it right there in the upper right-hand corner. F prime of x is going to be negative 2x plus 6. That was awesome. That was a fun little journey, right? Okay. So let's see. We're asked to find the derivative of this. So we use the limit definition. I did a demo on the shortcut. I didn't go into the details on how I did the shortcut, but I just did a demo on it. So all this work that we did can actually be done in like an instant. Give me just a moment. I want to clear this out. Delete. Okay, can y'all see that? I'm just curious. That's cool. What if I go like this? Oh, that's awesome. Just playing around with these new features. Style. And we want to go like this, a little bit thicker. Maybe this one. Yeah, that's fine. All right. So let's see, how do we do? This is the result that we got. I was trying to stall a little bit just to kind of recap and see if I'm missing anything. So then with this example, we see it start there. And let me turn off this guy. Okay. And we see the negative 2x. So the derivative of f prime is going to be negative 2x plus 6. Okay. It says find the derivative. Yeah, so I think we're okay. Okay, we're going to let that be. So let's look at this about derivative notation. For historical and practical reasons, several notations for the derivative are used. To see the origin of one notation, recall that the slope of the secant line through 2 points on the curve is going to be given by this, f of x plus h minus f of x over h. The quantity h is the change in the x coordinate, right? So the change in x. So if we wanted to talk about the slope of the secant, we could say f of x plus some change minus f of x divided by the change in x. In other words, this is like the y2 minus y1 over x2 minus x1, the change in y over change in x. So by letting the change in x go to 0, the slope of the tangent line is going to be given as the limit as the change goes to 0, f of x plus that change minus f of x over the change, which is going to be the limit as the change in x goes to 0 of delta y by delta x, which is dy by dx. The new notation for derivative is going to be dy by dx. It reminds us that f prime is the limit of the change in y over change in x as the change in x tends to 0. In addition to the notation of f prime and dy by dx, other common ways of writing the derivative include df by dx, d by dx of a function, the derivative with respect to x of a function, and y prime of x, right? The following notations represent the derivative of f evaluated at a. So this is f prime of a, y prime of a, df by dx in regards to a, and dy by dx in regards to a. I think that's it. Ooh. What's my time looking like? Got right at about 50 minutes. 50 minutes remaining. All right, let's keep it moving. Can we see an example? Yes, this is what we want to work. And let's go like this should be fine. And then let's do like this. It should be ready to go. No? Ouch. Ow. My dog is what? Come on. Come on. Come here. Come on. My dog don't know how to act, so she got a bath yesterday, so now she knows that she's like cuddly soft. She's not like so stinky like people aren't automatically like pushing her away like, stinky dog, get away from me. Like now we're not doing that anymore. So now she's just like wants even more attention. It's really funny. Uh-oh. Come on, I'm trying to get a text box. There it is. I'll do a space. I can go away and come back. There it is. And paper. We want it to be grid paper. Come on. And we want that to go like here. Oh no, are you not going to go on top? Look like it's not going to behave the way I want. Can I just paste it? Oh, can I do style? Nope, that's not what I want. Can't get this to behave the way I'd like it to. Okay, I'm gonna just write in the white space then. All right, so let's go here. So we're asked to compute dy by dx. Find the equation on line tangent. Okay, so again, a quick demo on the shortcut. So the square root of x is actually the same as x to the power of a half. So I'm just doing a demo on the shortcut. So then if f of x is the square root of x, then f prime, if that's to the power of a half, the half comes down. We're going to have x to the power of a negative 1/2. And that's going to be 2 times the root of x, 1 over that. And then that's going to be, if we rationalize, root x over 2x. I think that's what that is. So I'm going to say that this is my derivative there. Okay. I feel like I might need some more space. So since I feel like I'm going to need space, let's create some space. I'm going to get rid of that one. going to take this stuff here. Okay. I would like to take that and I'm going to add it. I think I want it on the previous page. Page 6. There it is. So let me add a page here. Where is my image? There it is. So I need to cut this. Nope. Cut. Come on. Paste. All right, let's give this one a go. All right. So now we're here. So I think earlier we just said that dy by dx, if we're not doing a shortcut, it's going to be, we could say, it's a couple of ways we can write it. We're going to do the limit as the change in x goes to 0 of f of x plus some change minus f of x over delta x, right? So as that delta x goes to 0. So then for our example, this is going to be, so we want to say x plus delta x. So we're going to say the limit as delta x goes to 0. We're going to have the square root of x plus delta x. So more than likely, I'm just going to do, let me see. We'll see. Is this, I don't know. I'm going to keep going. Let me not make it a statement just yet. So there's the x plus delta x into the original minus the square root of x over delta x, right? All right. So let's try rationalizing. Multiplying by the conjugate. So the conjugate, I'm going to multiply the top and bottom by the conjugate of the numerator. So we have this root of x plus delta x. What's the time? X plus delta x, we're going to say plus. So we're just multiplying by 1 in the form of the conjugate over the conjugate. Square root of x plus delta x plus this. All right, so we're just multiplying by 1. So now when we do this, the following happens. Let's just see. This is going to become the limit as delta x tends to 0. Now the top is going to become, x plus delta x, because basically it's the first thing squared. We're going to have the first and the outer essentially cancel, right? I'm going to skip that for now, but the first and the outer cancel. If I need to show it, we can do it another time. And I'm going to say minus, let me just show it. Just go ahead and do it. So the first times the first is going to give us, I'm going to write it like this. The square root of x times root x plus delta x. That's the first, that's the outer. And then the inner times the inner is going to be negative root x times x plus delta x. And then the last times the last is going to be square root of x squared is just going to be minus x, right? All over delta x. I think this is okay. So then what we notice is that this cancels this. If we go ahead and combine like terms, this is also going to cancel this. Looks like we get 1. Is that right? Am I missing something? I think I am missing something. Oh, the bottom, right? We still have this guy persist. Copy, paste, and let's just create a little bit of space. So that guy is still there, right? So we can't forget about that. Okay. All right, I think we're okay. So let's keep going and see where this goes. So it's an art of discovery. So I keep using the words like let's see and let's discover and things of that nature. All right, so this is going to be equal to the limit as delta x goes to 0. So it looks like a lot of stuff cancels there on top and on bottom. Let's see. Oh, okay. I see it. So basically, we have, nope. Here's the bottom. Paste. And the top. Paste. So we have delta x over this, right? And then you should notice something else happening. This cancels this. So now we're ready to pass the limit. So that means that this term is going to go to 0. And we're going to be left with, we got basically 1 over 2 times the square root of x. And I think that's what we got earlier, right? Oh, it's down here. Okay, my page is a little bit out of order. Yeah, 1 over 2 times the square root of x. And then if you rationalize, it'll be the root of x, square root of x over 2x. Okay? Let's see, we're going to go here, get rid of the grid. And I think it's a little bit out of order. So I want this guy to go here. Oh no. Come on. Yeah, we're good to go. Okay. No, we're not good to go. Alright, let's just get off of this. And it should, come on. Is it like, did it create a duplicate? dy by dx, I think it did create a duplicate. So let's just get rid of all of this. Delete, tag on it. Let's try this again. What? I gotta figure this out. Give me a moment. It is kind of acting up. What if I go like this and I come back to it? That fixed it. Yeah, I don't know. It was just kind of bugging. All right. So I think we're okay there. Here's the work that we just did, and we got a result of square root of x over 2x. We did a shortcut and a long cut. And then if we, we'll come back to number 3 in just a moment. And then find the equation of the tangent line. I'll just use this for now. The hardest part is over, right? We see we have the 1 over 2 root x, so they didn't rationalize, which is fine. And then the slope of the tangent line at 4, 2. So when x is 4, evaluated when x is 4, we can see here. When x is 4, we're going to plug in a 4. Square root of 4 is 2. We get our 1 over 4. So then that's just the slope of the tangent line. So then, you know, from college algebra, you find the equation of the line. Okay. What's the time? Let's go ahead and do example 3, right? That was a little involved. I'm going to leave that one as an exercise, okay? I'll kind of glaze through it a little bit. If you want me to work through it, I can work through it. You'd have to reach out to me, but I'm going to leave this one as an exercise, okay? We can kind of mention it though. So if we let our function be 1 over t, we want to find the derivative. Now, I do want to kind of mention the shortcut here. So if we were to do the shortcut, if g of t is equal to t to the negative 2, then that means that g prime of t should be negative 2t to the negative 3. Okay, hopefully you can notice the pattern. And then the negative exponent, this is ultimately negative 2 divided by t cubed, and you actually see it over there. All right, that was just a demo on the shortcut. Okay, I'm going to kind of let that be for now. Okay. Sketch the graph of f prime from the graph of f. Okay, so in this example, if we look at this graph, right, what's the slope the slope of the tangent line, the slope is what? -1, and then it's +1, and then it's -1, right? So then the slope there, the graph of that one is going to be here in red. See, notice that the slope is -1 first for all of this is -1. Then the slope is +1. Then the slope goes back. Oh, it's not actually -1 again. It's negative what? It's -1, 1/2, right? -1/2 is here. Okay, so the graph of the derivative is going to give us a sense of the slope of the tangent line for any given x. Okay. Sketch the graph of g prime using the graph of g. See figure 3.2. Okay. So if we get a sense on the far left, let me see. I think I can kind of do the following. So if we consider the tangent line over here, right? So notice that the slope is positive, and then it zeroes out when you get to about right there. So the slope zero. So the slope hits 0 there, right? So we know that if we were graphing the derivative, it should be at 0 when x is -3. Then the slope goes negative, and then it goes back to 0 right there. So the slope should also be, so first the slope was positive, first the slope was above the x-axis, then it was at 0, then it was below the x-axis, then it went back to 0, then it goes positive, 0, negative, right? So here, let's do it like this. If we consider like where it flattens out, right? So it flattens out there, that's going to be a 0 there. There's going to be a 0 here. There's going to be a 0 here, all right? So notice on the far left, the slope is positive, so we should be above the x-axis. Then we're at a 0. Then the slope is negative, so we should be below the x-axis. Then we should be back to 0. The slope is essentially positive, so we should be above. And then the slope is 0 here, and then it should be negative. Let me think about this. Yes, right? We have 1, 2, 3 turning points, and then we have 1, 2 turning points, right? And it should finish negative. So it's like the power is going to go from a power 4 function to a power 3 function. So we can kind of anticipate something that behaves in this fashion. The slope will be, it'll be here, and then something like this, something like that, and then we're going to finish like this. So we can anticipate something of this fashion. Okay. So let me kind of come here. And you see it down there in the red. See, it was positive, then it was 0, then it was negative, and then 0, positive, 0, and then negative. Same kind of articulation that we did. Okay. So I'm going to leave those there and kind of move on. Asymptotes. Graph the graph of the function f is shown. Sketch the graph of the derivative. Okay. So again, we're always considering the slope of the tangent line. So notice that the slope starts off negative, then it goes really negative. An asymptote is going to persist. So if we have an asymptote, it's going to stay when we go from one function to another. So if we're considering the key points, the asymptote is going to stay. So I'm just going to put a star there for that. This is also going to stay. We should have a 0. It kind of flattens out here. So we should have a 0 right about here. Right? So this should be 0. These are going to be our asymptotes. So those are going to stay. This is going to stay. And I think those are the key ones, right? So first the slope starts off negative. So to the left of this asymptote, the slope is negative. Between the asymptote and 0, the slope is negative again. So it's over here, right? Then it goes to 0. Then the slope goes positive. So between these two key points, we're going to be above the x-axis. The asymptote persists, and then the slope goes back to being negative. It goes from being really negative to just a little bit negative. Open that positive, negative. So let's see. It goes from being just a little negative to really negative. So we can still anticipate the graph to behave like that over here. We're going to go from negative to positive. So we're going to go from here to 0 to a positive, something like that. That's what we can anticipate. And then from really negative to not so negative. So it's going to go here and then finish off like that. So we can anticipate a graph like you see there. Let's see, how do we do? So again, what I'm doing is I'm visualizing the slope of the tangent line. and you see it in red there. Okay, so you have to do the best you can there. I know that's a little bit abstract. You just have to do your best. Okay, this is also the reason why why I switched it over to Pearson, because Pearson typically gives an explanation for each question. I went on and just did Pearson because I know how to work Pearson, and trying to learn Cengage in a split moment like that, it wasn't going to work for me. I was going to be stressing myself out. And then if I'm stressed out, I know it's going to be amplified in you all. So to kind of help you all, I calmed myself down. I was like, let me just use something that's familiar. And that's why I went to Pearson. Okay, so I say that because, again, all the homework questions typically come with an explanation. That question help tool is how you get through it. You want to definitely make use of the view and example. It comes with the e-textbook right there with each question. It'll put you right in the book where the question is coming from. And then also make use of the Ask My Instructor. Okay, so when you make use of the Ask My Instructor, I'm gonna look. So it'll take a screenshot of your question, and it'll send me the screenshot of your question directly in an email, and I'll load it to my tablet, and I'll walk you through the questions that you all are asking. Okay, so we're gonna let that be. We have this theorem. If f is differentiable at a, then f is continuous at a. All right. We have a proof. Let me see. Because f is differentiable, then it should be the case that f prime is going to be the limit as x approaches a of f of x minus f of a over x minus a. That's going to exist. To show that f is continuous, we must show that the limit is equal to f of a. The key is the identity. So if we look at f of x, let me think about this. Oh, notice that f of x is going to be equal to, we have this function times x minus a, right? Or as long as x is not equal to a. Taking the limit as x approaches a, okay, plus, we're going to let that go. Let me see. Taking the limit as x approaches a on both sides. Those cancel. That goes to 0. That's going to be f prime. That goes to 0, and that's going to be f of a. And 0 times the prime gives us just f of a. Okay, that's a proof. That's okay. Let's try. Let's get this theorem. Not continuous implies not differentiable. If f is continuous at a, then f is not different. If f is not continuous at a, then f is not differentiable at a. It is tempting to read more into theorem 3.1 than what it actually states. If f is continuous, f is not necessarily differentiable. But, so differentiability implies continuity, but continuity does not imply differentiability. Like the reverse is not necessarily true. Just because the function is continuous does not necessarily mean that it's continuous. For instance, we have examples here. The black is the original, where even though the function is continuous, there are no holes, gaps, or breaks, but there is a sharp corner. So we can't really do differentiability at sharp corners or things of that nature. So even though this function is continuous, it's not necessarily differentiable at all points. Here are some more examples of the function is continuous, but not necessarily differentiable. Okay. What's my time looking like? We got about 30 minutes or so. I think I'm going to get to the end of whatever slides I have here and call it a day. Let me see, what are we looking like? I think this might just be section 3.2, which is fine. So when is a function not differentiable at a point? A function f is not differentiable at a point a if at least one of the following conditions hold. F is not continuous at a, so if there are any holes, gaps, or breaks. If f has a corner, as in figure 3.25, or if f has a vertical tangent, like in figure 3.26, okay? So that's when the function is not going to be differentiable at a point. So we have this example. Let me see. Find the values of x on this interval in which g is not continuous. Find the values on this interval in which g is not differentiable, and then sketch the graph of the derivative. Okay, so on the left we have the graph. Where is it not continuous? So it's not continuous when x is -2 and at 2, right? At -2 and at 2, right? So there's a gap or a break at when x is -2, and then there's a hole at x equals 2. So those two locations, the function is not continuous. So if it's differentiability does imply continuity, but And then the contrapositive of that, if it's not continuous, that means it's not differentiable. So that means that we can say this function is not differentiable at those points. But we also have another point where the function is not differentiable at 0. So we have 3 points. So we say because it's not continuous at plus or minus 2, that means that g is not differentiable at these points. Furthermore, g is also not differentiable at 0 because it has the cusp, a sharp corner, right? And then sketch the graph. So that means that the derivative is going to be undefined when x is 2, when x is 0, and when x is negative 2, 0, and 2. On the far left, notice that the slope is positive, then the slope is negative. So on the far left, we need to be above the x-axis, and it's constant. On the right, the slope is negative and it changes, so we need to be below the x-axis, and then it gets really negative. And then on the right, the slope is positive, and it's approaching 0. And then on the right side of that 0, the slope is close to 0, then it goes off steep. It gets more and more negative, more and more steep. Okay, so that takes a little bit of practice. Actually, what's next? What's after this? Is that it? Oh, those are just extra pages. I don't feel like 20 minutes or so is enough to kind of get to the next section. So what I'm gonna do, I'm actually gonna stop here for today. Actually, you know what? Yeah, I think I'm tired. So we're gonna do the following. Let's see, what do we have? So those were just a bunch of extra pages. I didn't realize that. So we're gonna actually stop this presentation here, and we're gonna end here. A few notes. I am available all day, so you can pretty much just reach out to me. I'll be monitoring my emails, responding to emails, and kind of updating my gradebook and my records. I'll do my best to try to follow up with students that I see might be missing assignments and just say, hey, are you okay? Are you able to access the material? So I'll be kind of looking for that. Be on the lookout for a quiz. So I know that Pearson was kind of acting up. The main thing is I just want you to do your best with this material. Just get it submitted. At the end, if you feel anything, we can talk about it, and I'm open to negotiations for stuff because I realize that this is a little bit out of the norm, so it's okay. Okay. I just want you to do your best, get your assignment submitted promptly. The more prompt you are, the better, and we'll kind of work it that way. Whenever you see any kind of assignment on Pearson, just go ahead and get it done. And again, I'm open. I'm open to negotiating about some of these things. If it's too much or whatever, just talk. Okay. All right. On that note, we're going to end this session here. And from one beautiful mind to another, enjoy the rest of your day. You! So I get that from Infinite Waters, Ross Smart. I had to give a shout out to Infinite Waters. That's a phenomenal brother. Like he's just posts videos daily, and he basically became a millionaire by saying, "Peace, Infinite Waters, diving deep once again." So yeah, I like listen to him. A lot of times when I go running, I'll put him in my ear, and just he just has a lot of phenomenal material. So just check him out. Yeah. And again, we're gonna end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.